Welcome back. So the last time we were looking at some linear algebra, we recalled what vector spaces were, gave some examples, the notion of dimension, basis, etc., and we defined linear maps and gave a couple of examples. So the first example we gave for linear map involved a matrix, right? I mean T of x equals AX. Okay, where this was an m by n matrix, this was an n by 1 column vector, and the resultant thing was an m by 1 column vector. It turns out this is the most general example of a linear map in some sense. In what sense? So suppose V and W are finite dimensional vector spaces, and let's say we have two bases. Suppose they are ordered bases. Suppose E1 to En is a ordered basis of V. What is an ordered basis? It's simply a basis, but you're just writing them in a specific order, right? So it's not really a set. A set doesn't have an order associated to it. And let's say we have a basis for W. Let's call this basis F1 to Fm, ordered basis of W, right? And let's say T from V to W is a linear map, yeah? So in other words, suppose you take any general vector V in capital B, then V is some linear combination of these EKs from 1 to K, 1 to N. So T of V, by what I mentioned earlier, turns out to be this, yeah. So in other words, if we know what T of Ek is, we can determine T of V for any V, right? Now T of Ek is an element of W, so in particular it's a linear combination of these basis vectors, right? So suppose I write T of Ek as sum over j from 1 to m T j k f j, yeah. These T j k's are scalars, right? By the way, it might puzzle you as to why I am writing j k f j as opposed to k j f j. You will see so in a moment, yeah, but this is just convenient for our purposes. So once again, so suppose T of Ek is sum over j T j k f j. Then so T of V, which is T of sum of Ck Ek, equals sum over k T of Ek, which is sum over k sum over j T j k C k f j. In other words, if I interchange this summation, which you can do with impunity when the sums are finite, you can't, by the way, if the sums are infinite, this resulting vector is a linear combination of these fj's. The coefficients are given by this, right? In other words, if you take V and if you consider the coefficients of V is of course sum of Ck Ek, as a column vector of scalars, and if you write T of V as some linear combination of the fj's, and you consider those coefficients also as column vectors, yeah. So this column vector is precisely this matrix times this column vector. In other words, recall that the first example of a linear map we gave was precisely this. In other words, every linear map between finite dimensional vector spaces secretly arises via multiplying a matrix with a column vector, except that the data you need to do this is the choice of an ordered basis for V as for the domain as well as for the target. If you give me an ordered basis here and there, then I can come up with a matrix that encodes all the information in the linear maps. In other words, let's call this matrix by this symbol. Morally speaking, I must give you the ordered basis here and the ordered basis there, because for different ordered bases you can get different matrices. So given the linear map, you get a matrix. Given the linear map and ordered bases, you get a matrix, and that matrix obviously depends on the linear map as well as the ordered bases. Likewise, given any old matrix, you can come up with a linear map provided you choose ordered bases. So there's a correspondence between these two pieces of information. Yeah? Right. So the point is, if you choose a different basis, then you will get a different linear map. Different choices of bases give us different linear maps. Yeah? Okay. In fact, it's even if you take the same say different, not linear maps, different matrices, even for the same linear map. For the same linear map. Okay. Sorry about that. Even for the same linear map, you get a different matrix. Yeah. Okay. So how does one determine the matrix of a linear map? Point 1. And if we change bases, how exactly does this matrix change? Okay. So these are again standard things, but let's look at the quote unquote algorithm to come up with a linear matrix. So suppose I choose this data. How does one come up with the associated matrix? Right? What's the procedure to do it? So what you do is you take T of E1. Yeah. This is a linear combination. This is a linear combination of FIs. Right? You arrange the coefficients as a column vector. Right? Likewise, T of E2 is a linear combination of the FIs, and therefore you can arrange its coefficients as a column vector, and so on. The matrix T is simply the column vector corresponding to T of E1. The column, that's the first column. The column vector corresponding to T of E2 is the second column, and so on. Yeah, that's the algorithm stated abstractly. Let's actually apply it in a concrete example so that we are all on the same page. Right. So for example, suppose you take a linear map from R2 to R2 given by T of xy equals, let's say, a simple linear map 2x and 3y. Yeah. Why is this a linear map? Please think about it. Why is it a linear map? Again, please answer this question to yourselves. I mean, this is a very basic thing. So what does the algorithm say? So you need to choose bases here. So let's say we choose E1 and E2 to be the standard basis vectors for R2. And here, let's choose the basis to be, let's say, E1 plus E2, which is 1, 1, and E1 minus E2, 1 minus 1. Why is this a basis? Please think about it. Okay, this is F1 and this is F2. Okay. So what is T of E1 again? T of E1 is 2, 0, which is equal to what? It is 1 times E1 plus E2 plus 1 times E1 minus E2, which means it's 1 times F1 plus 1 times F2. So the column vector corresponding to T of E1 is the collection of coefficients 1 and 1. Likewise, T of E2 is 0, 3. So this equals 3 divided by 2 times E1 plus E2 plus minus 3 divided by 2 times E1 minus E2, which is minus 3 divided by 2 times F2. So this is 3 divided by 2 minus 3 divided by 2. So the final matrix is simply putting these together. This is the matrix. Yeah? So a very simple example. Now what happens if you change the bases? I'll come to it in a moment. But for now, let us look at one more important concept which we've been using all along anyway. So matrix multiplication. How do you multiply matrices? Yeah? Matrix multiplication. Right, so I want to define matrix multiplication. Although you would have seen matrix multiplication in high school, my aim rather is to motivate why matrix multiplication is defined the way it is. Yeah? That's not the only way to multiply matrices. I mean, the way that we are all familiar with. I mean, for example, you could have potentially defined matrix multiplication as, let's say, give it by a different name, let's call it a circle instead of a cross, let's say 5, 0, 0, 10 or whatever. You could have potentially defined it in the following way. You could have multiplied it entry by entry, right? This is not the way to multiply matrices, right? This is not the usual way to multiply matrices, but you could have defined it like this. And indeed, this definition is also useful in certain contexts. Okay, entry-wise multiplication has also been studied in mathematics. But typically, we don't deal with it. We use a slightly different definition, right? Why is that so? Okay, so if you take V, W, and X, and if they're all, let's say, vector spaces, finite dimensional vector spaces, and let's say we choose ordered bases, let's say E1 to En, let's say F1 to Fm, and let's say G1 to Gk or Gl, right? Or maybe Gmno. Okay, let's say G1 to Go. Let's say these are ordered bases, and suppose T from V to W and U from W to X are linear maps. Now we get a matrix for T and we get a matrix for U as well. Now you can verify that if you take the composition of two linear maps, firstly you get a linear map. Secondly, it turns out the matrix for the composition is indeed the product of the matrices in our familiar sense. That is, you multiply matrices in the usual way. The ijth entry is sum over k, a I k, b k j, right? This is how we generally multiply matrices, right? And it turns out indeed the matrix for the composition is the matrix multiplication of these two in our usual sense. That is the point of defining matrix multiplication the way we usually define. So why is that so? It's not difficult to derive. So suppose I take U of T of, let's say, EI, right? This is U composed with T of EI. U of T of EI is what? It is U of, what is Ti? It's a linear combination of the Fj's given by this. So you can pull this out. And what is U of Fj? It's again a linear combination of let's call this, sorry, Fji, right? It's not K. Maybe I'll write it like this, and then what is U of Fj? It's a linear combination of the GKs, right? So if I put these together, basically it is UKJ TJI GK, right? So in other words, it's sum over K, sum over J, UKJ TJI GK. This is the matrix corresponding to U composed with T, and indeed it is the matrix multiplication of U and T the way we define it normally. Okay, that's the point. This is so that's the point of defining matrix multiplication the way it is usually defined. Okay, all right. So matrix multiplication satisfies a bunch of standard properties, as we all know. So matrix multiplication satisfies these properties. A times BC is AB times C. That is, if you multiply BC first and then multiply with A on the left, that's the same as multiplying AB first and C on the right. Okay, AB is typically not equal to BA. Indeed, first of all, AB could make sense, right? When can you multiply matrices, by the way? Recall, if this is m by n and this is n by p. Okay, if the number of columns of the first one is the same as number of rows of the second one, only then can you multiply matrices. So for example, BA need not even make sense, and even if it does make sense, these two may not be equal to each other. Okay, so this is an important little point. And of course, matrix multiplication respects addition. That is, this property of distributivity exists. So this is associativity, and this is distributivity. Yeah? Okay. So here is, and I might as well take the opportunity to make, so a square matrix is one where the number of rows and columns is the same. The identity matrix I is basically the usual one with zeros everywhere except on the diagonal. Okay, this is the diagonal of the matrix. Right. Now, so suppose, so here is one definition, if you wish. The transpose of a matrix, so A transpose Ij is simply a Ji. In other words, you simply interchange the rows and the columns. So an m by n matrix becomes an n by m matrix. Now, if you take A and B and you take the transpose of their product, that's the same as B transpose A transpose. Okay. As a sanity check, if this is m by n and this is n by p, we can multiply these two and get an m by p matrix, and the transpose will make it a p by m matrix. This will be p by n, this will be n by m, and so we get a p by m matrix. So the sanity check does work. Okay. Now, akin to transpose, if the matrix consists of, let's say, complex numbers, consists of complex entries, we can define the Hermitian conjugate, which is very similar to the transpose, except you have a bar on it. Yeah. And likewise, if you take A times B, the conjugate, that's the same as B conjugate A conjugate. Yeah. Now, one more definition. a symmetric matrix. What is a symmetric matrix? It is one that equals its transpose. In other words, Aij equals Aji. And a Hermitian matrix is one that is equal to its Hermitian conjugate, that is Aij equals Aji bar. Okay. Right. One more definition. Why must we care about the following definition? We'll see it later. I mean, since this is just a review, I'm not giving you as much motivation as I would have normally for these sorts of things. So an orthogonal matrix A is a square matrix such that A times A transpose equals A transpose times A is the identity matrix. Yeah, and a unitary matrix is the complex analog of this matrix. U is an n by n complex matrix such that U conjugate U equals identity. Yeah. Right. So that's that about matrix multiplication. Now let's return to this question as to what happens if I choose a different basis, right? So if I have, let's say, a vector space V and a linear map, and let's say I have E1 to En and F1 to Fm. If I change these ordered bases, the corresponding matrix will certainly change. And how does it change, right? Okay, what we will do is we will recall the answer to this question when V and W are the same, because that's the case that we will use often in this course. So suppose you have a linear map from V to V itself, except you're choosing two different bases. Let's call them E1 to En and F1 to Fn. In fact, why don't we actually take E1 to En? That gives us a matrix T, but in this basis, both sides, the basis is the same. Now the same thing, but if I choose a different basis, but the same basis for both, okay, so then I'll get a different matrix. Okay, rather than writing it as T and the subscript, I'll write it as, let's say, T and let's say maybe T tilde, okay, or actually, since there are too many T's and T tildes, let's call this A and B. Yeah. So the same linear map, except that I'm choosing these two to be the bases here and these two to be the bases here. I'll get two different matrices. Yeah. So then, sorry, how does one change the basis, right? So these E's themselves, EI is a linear combination of Fj's. So in other words, EI is some linear combination Sji times Fj. Okay? For scalars Sji. Right? Now we need this information. So again, once again, EI is sum over J Sji Fj. Yeah. Right. So suppose I take a vector V. In the old basis, it is sum over I Vi Ei. In the new basis, what would it be? Well, I can write the EIs from this equation as sum of Sji Fj. In other words, if I interchange the order of summation, it's Sji Vi times Fj. In other words, this column vector, which represents V in the old basis, changes to a new column vector in the new basis, let's call it W if you wish. Okay. This is given precisely by the matrix multiplication of the old column vector by this matrix formed by these scalars. Okay. That's, by the way, the point of choosing this awkward convention. Naively, you would have written it as Sij times Fj, but the reason behind writing it as Sji times Fj is to get this rather pleasant consequence. That is, if you change the basis, the old collection of components is the change of basis matrix times, the new collection of components is the change of basis matrix times the old collection of components, and by change of basis matrix I mean the scalars that I used to change this old basis, that I used to get the old basis in terms of the new basis, right? Okay. Now if I take V, again it's represented by a column vector, so suppose I take TV, right? We just agreed that TV corresponds to multiplying this column vector by the matrix T A, yeah. Likewise, if I take the same TV, it will correspond to multiplying by the matrix B in the F basis. This is in the E basis, right? So how are these two related? They're basically, how are they related? Well, what is this? So this vector, how will I get, what's the relation between this column vector and this column vector? Recall that the column vector in the new basis equals S times the column vector in the old basis. So in other words, S times AV would be the column vector in the F basis, right? Would be the column vector in the F basis. But V is the column vector in the old basis. So S times A S inverse W equals BW, which means B equals S A S inverse. Okay, so this is the crucial little equation that we get. If you change your basis, the matrix will change by S A S inverse for some invertible matrix S. What is an invertible matrix? Well, what is S inverse, right? So just to take a step back, a matrix A is invertible if there exists a matrix B so that AB is a square matrix, is said to be invertible if there exists a B so that AB is identity. It turns out if AB is identity, then BA will also be identity, okay? And this B is written as A inverse and it's called the inverse of the matrix, okay? And just as in the case of transpose, AB's inverse is B inverse A inverse, okay? Not every matrix is invertible. Obviously the 0 matrix is not invertible because 0 times anything is 0, it can never be identity. But for those matrices that are invertible, we can talk about their inverses, right? Again, so coming back, I just recall the definition of what invertibility is so that we are all on the same page. So in the previous, so what we were talking about previously, if S is a change of basis matrix, by the way, S is invertible. This matrix S is invertible. Why is it invertible? You can pause your video and think about it, but the point is it's invertible because you can reverse this transformation. You can write f also in terms of E, right? So if you write E in terms of f and then f in terms of E, then you're writing E in terms of E, which means it's doing nothing, right? It's the identity map. So in other words, since the composition of two linear maps, since their matrix, their associated matrices get multiplied as in matrix multiplication, S is invertible because there is another matrix which when multiplied with S gives you identity, okay? Anyway, so this is very crucial. If you change your basis, the matrix will change like this. This is called a similarity transformation between matrices. A and B are said to be similar if this happens, okay? If they represent the same linear map but in two different bases, okay? So we'll end now and thank you for joining.